Okay, so a new beginning. I have a function, I'm trying to find the root, so I just shoot some number. And now we want to take into account the shape of the function. So let's say that the value is somewhere here, and let's say that the function goes like that. Now I'm trying to get to the root, which I can see over here. And when you look at this picture, you might say, okay, I'm sitting here. So presumably I have a lot of information about the function at that particular point. And perhaps I could take the tangent line. And if I take the tangent line, it must intersect with a little bit of luck the x-axis. And I think, naively, that it's a better estimate. And I'm sitting here now. Did I get closer to the root? Yes. Does it look like a good idea? I think so. Let's try it again. I take the tangent line, and I got so close to the root that I cannot even write the name of the new number properly. So this looks like a killer method. This looks good. And the next tangent line, I cannot even draw the picture properly. That's how close to the root I get. So this looks like a very nice method. Let's try it. Our test function is x cubed minus x minus 3. And let's say that my initial guess is 5. So we already calculated how much is a 5. Do I remember it? I think it was 110. 125, 120, oops, there was 10 here. Got carried away, sorry. There was 10 here. 25, 20, 110, yeah. Where do I get the tangent line? I don't feel like doing it each time again and again, so let's do it in general. I have some point here, which I'm going to call xk. And I'm sitting here. And then the value, the elevation, is fxk. And of course we know the slope. The slope is the derivative of f at xk. That's the data that I need. I have a point through which the line goes, which is here, and I have the slope. I can write down the equation. The tangent line, well, there are several ways how to write equation of a line. Probably each has his own or her own preference. My preference goes like that. At a certain x, the elevation on the line is given by the original elevation. And now there is the slope. And there is the movement along the x-axis. That's how I prefer to see a line. Okay, let's see. That's a tangent line. And I'm looking for the intersection with the x-axis, which means I'm putting y equal to 0. So I'm going to rearrange it somehow and solve it for x. So I will move fk to the left-hand side, and then I divide by the derivative. So minus fxk over f prime xk is equal to x minus xk. And then I move xk to the left, and I get a nice formula. So that's my new xk. In this case, it's xk plus 1. That was nice and easy. Okay, let's use it. So I need a derivative at xk. What's the derivative? It's 3x squared minus 1. So when I'm sitting at the point 5, the derivative at 5 is 25 times 3 is 75, 74. Ooh, I was hoping for something better. Because now I have to divide. It's going to be ugly. Okay, that's life. What's x1? x1 is 5 minus 110 over 74, which is 5 minus, I don't like it, 37 by on the top 55. This is divisible by 5, and this one not. This is divisible by 11, and this one isn't. That's it. Well, I guess I could use a common denominator, but I don't feel like it. 5 times 37, okay, that's okay. Good enough for me. So that's x1. And now we should calculate x2 in the same way, and so on. You can easily imagine how the calculations would go. Again, why am I doing it by hand? First of all, we get to appreciate the workings of this algorithm. Second of all, we are preparing for the exam, because on the exam, it may happen that you are given a function, you are given a starting point, and you will be asked to show how the Newton method goes. By the way, the same can happen with the bisection method. I can give you a function, a starting interval, and ask you to show me several iterations by hand to show me that you actually know the workings of the algorithm. Or perhaps I could ask for the explanation of the algorithm with a picture. I can ask for this procedure. I can ask for explanation of the bisection algorithm. These are two basic algorithms for this course, and I want you to know them quite well. Back to the question. By the way, there is a third reason why I'm doing it by hand. It's a tribute. It's a tribute to people who, let's say, even in 1950s, were sitting somewhere with huge sheets of paper and pencils and doing calculations like that for life. Because at the time, the computers were not widespread. They were just starting. And until all the way up to, let's say, 1950s, people were doing calculations like that by hand. And now you can appreciate that it was a really hard job. By the way, these people were called computers. So, yeah, we are lucky, but anyway, we can appreciate that they wanted an algorithm which runs fast. You don't want to spend half a month doing calculations like that, definitely not. So, is this algorithm fast? That's a good question. First, we are going to give it a name. This is commonly called Newton algorithm, but there are also some other names for it. And I'm not going to take sides on any names. If I had my way, I would call it a tangent method, because we are using tangents. Yeah, tangent method. Everybody would know what it means. But it's called Newton method, or Newton-Raphston method. Or, yeah, I don't want to go into it. Anyway, here we go. We have a function which is continuous, and it must be also differentiable. Otherwise, we are in big trouble with the formula. So it must be also differentiable. And we have a tolerance. We just choose some x0. Just shoot from the hip, some number. But if we, for instance, can plot the function, we can make an educated guess, which would be better, but that's another story. Okay, we choose some x0, it becomes xk for k equal to 0. And then there is a formula which tells us how to calculate the next approximation. And by a remarkable coincidence, it's exactly the same that I have here. So I was good. Okay, let's skip the next part yet. So we have the procedure, it's called the Newton method. Now, what can we expect from the Newton method? Let's make a little comparison. And let's make a little experiment as well. So, I have a little code here. Let's make it larger again. So here's a code. I'm asking for the root of our function f. I'm starting at 0 for some reason. I started here at 5. Let's start at 5. And I'm using the Newton method, and the tolerance is 0. Well, that's 10 to negative 4, just like I did before with the bisection method. Let's fire it up. Wow, just 6 iterations. That was nice. That was very nice. Let's try 10 to negative 7. Wow, just 6 iterations. Is that weird? Is there some error? Probably no. Actually, the quality improves so fast that if we ask for 3 digits correct, essentially, we also get 7 right away. There is no reason for Newton method to stop earlier, because the improvement is so vast in just one iteration. If it stopped in iteration 5, then the error will be larger than 10 to negative 4, and the next iteration already has a very nice small error. So that's a wickedly fast algorithm. Let's put it here, fast. reliable. Reliability, well, unreliable, unfortunately. What can go wrong? Well, first of all, technical problems. If you don't have the derivative, you are out of luck. It may also happen that you are happily running using your tangent lines, and then suddenly you find derivative equal to 0, which means horizontal tangent line. Of course, horizontal tangent line will never intersect the x-axis. You're out of luck. These are not fatal problems. I mean, this is not a fatal problem. You can just start at a different place with your x0, and you hope that you will not reach this place. So in practice, this is not such a big problem. But there is something else. First of all, the Newton method, as it goes by the tangent lines, jumping around the graph, it likes to wander. Let's start at 0. Now, perhaps first, let's have a look at this column with axis. We started at 5, and we very steadily went all the way to 2.3 and so on. If I start at 0, that was unexpected, probably. Let's have a look at it. From 0, we go to -10. Why? I have no idea. The root is not there. Anyway, then it goes back to 0, and then it jumps all the way to -65, and then it goes to 0 again, then it goes to 4, so it overshoots, and then it settles down to 2.3 and so on. So it was going left, right, and so on. Yeah, it likes to walk around, take a look at the countryside and so on. That's typical of Newton, unfortunately. It can get even worse. Imagine this. Imagine that there's an asymptote, but the function never actually touches the x-axis here. Now, if you're unlucky, your initial guess will be here, and the Newton method will go here, and here, and here, and so on. It keeps taking tangent lines and goes all the way to infinity. It never goes to the root r. Another bad shape is Camel. If you are really, really unlucky with your initial guess, your tangent lines start jumping right here, moving left and right in the saddle. You will never get out to reach these roots. So essentially, when you are using the Newton method, you should be careful and you should watch what it's doing. So we definitely want to have some bound on the numbers in the calculations. So there is one of the things which is incorporated in the procedure that I'm using. If the numbers get too large, the procedure stops and tells me about it. And then it's up to me whether I want to continue or not. I have to make the decision, I as a human being. The same thing is here. There is a restriction on number of iterations, and if by a certain stage we don't get at the root, the procedure stops automatically. And of course I can change this bound. So if I feel that I'm on the right track, I can say, okay, you go longer. But I have to control the Newton method. Here is another nice example. Square root of x. We all know square root of x. Now let's imagine that I create a function by flipping it around twice. So this is an odd function. Now what's so special about it? If I start here and I make a tangent line, then my picture is not okay. It's too flat. I ran out of room. Okay. But in the actual picture, which would be correct, the tangent line intersects at exactly -xk. And by the symmetry, when you make the next step, you go back here. So when you start the Newton method on this function, it will just go left, right, left, right, left, right, never stopping. So you can easily throw off the Newton method. It's unreliable. On the other hand, this picture looks really nice. We started and yeah, it looks very nice. So there are some circumstances, and of course mathematicians are curious people, and they like to have certainty in situations. So they were able to identify situations when the Newton method actually converges. Just to give you some example, here we go to the slides. So I'm not really going to work with this theorem, so it's up to you just to read it and see what are the inputs in it. So we have a functional interval where it changes sign, which is actually here. That's a good news. And now on this interval, there are some assumptions. And if you translate these assumptions into ideas, what you learn is that on this interval, the function must have good enough monotonicity and a certain concavity. It has to be concave up or concave down. Doesn't matter which one, but it has to choose one and stick with it. We don't want to see the function to wave. And then if you get lucky with your initial guess, you are guaranteed to get the answer, which is the last line. It says, the sequence generated by the Newton method converges to a root. So in some situations, we are guaranteed to get the root, but it's not easy to get to them, as you can see in the picture. What people actually often do is to combine these two approaches. We have a method which is slow, but it's reliable, and another which is unreliable, but hopefully fast. We will talk about it later. So what people do, they start with a bracketing, they narrow down the root, but they are not going to go to extremes. They just narrow it down reasonably to get a nice situation. And in the nice situation, you apply the Newton method and you get very fast, a very good approximation. So there are different strategies that people use. Anyway, let's go back. Unreliable, in some situations there is a theorem. Error control. No error control. And that's pretty serious. But again, that's typical of numerical analysis. We don't know the right solution. So if we don't know it, how can we specify or calculate the error? That's a problem. What's the data here? We have some function and we have some points on it. How do you find the distance to the actual root? Well, essentially we cannot. So that's a big problem. There are some tricks that can help sometimes, or some situations that can help. Let me show you one. It's called fact because it's actually fairly simple. And let's translate it into ideas. We have a function, we have a root, and there is a neighborhood of a root where something happens. Now, what is happening on the neighborhood? The function is differentiable there, so it's nice, it's smooth, it doesn't break sharply. And the derivative is bounded away from 0. We are pushing it up using some constant m1. And this constant m1 should be positive. You'll see why. So here's the picture. There is a root, and something pushes the derivative away from 0. What does it mean? Well, practically speaking, it means that the function has to be rather steep. It shouldn't be flat, because flat functions have very small derivatives. Now, what does it say? We take some approximation of the root, which is over here, and we get some value. Now remember, the technical assumptions, this inequality m1 is less than or equal to the derivative, they tell me that the function is going rather steeply down or up. We don't know. In this picture, I want to see an increasing function in this picture because it's supposed to have a root here. Remember, so it's increasing. So it's very sharply increasing. If it's sharply increasing, it cannot go like that. It's forced to go at some angle, which can get also larger. We don't know. There is no bound from the top, but the important thing is there is bound from below, so the flatness is forbidden. This function has to grow at a certain rate, at least even faster. Now, if I know this distance, and if I know this extreme bound for the flatness, I can calculate from here the maximal possible error, the maximal possible distance between the approximation and the actual root. That's the geometric idea. Now, how do you prove it? The answer is very simple. You just apply the mean value theorem to this interval, r hat. Let's try it. Mean value theorem, how does it go? Like that. Fr minus Fr hat divided by r minus r hat is derivative at some mysterious point psi. Now we are going to apply absolute value. So I'm applying absolute value here. I'm applying absolute value here. And also here. Now the mysterious point psi happens to be between r and r hat. So they all live in this neighborhood u. So definitely the derivative is bounded from below by m1. Now you can see, but it's useful to have bound from below. We are pushing this whole thing up. Now, I can move r minus r hat to the right, I can move m1 to the left, and I get the following. I get that r minus r hat is bounded from above, which is the useful bound, and that's actually the error of approximation, by 1 over m1, and this difference, but actually r is a root, so this number is 0, so there is just the value. So if we get lucky and we get information about the derivative, then we actually can compare the actual error and the value of the function. So how do we know when to stop? Well, we simply wait for this number to be less than epsilon. And we are done. So that's nice. And it's actually also a nice reminder of the mean value theorem, which is also nice. But in applications, you very often don't have this information. So it's not that nice. So what do we have in general? And the answer is nothing really. So how do we know when to stop? Well, we guess. So what people do, there are 3 traditional stopping conditions. It's called stopping condition. Let me put them here. The first stopping condition is the absolute difference. When you calculate the next approximation xk, you ask how much it differs from the previous one. And if they differ just by a little bit, you can get optimistic and you can say, okay, so I'm probably close to the root. But of course, that need not be true, unfortunately. But it's probably the most popular stopping condition. Sometimes people work with relative difference. This makes sense if the approximations are really, really, really huge. It does not really work well if those approximations are close to 0. But sometimes people use relative difference. By the way, in books, people call it absolute error and relative error. But I don't think that's a good name because it suggests that it has some connection with the actual error of our solution. It does not have any connection with the error of our solution. The last stopping condition that people use is the value. That's also fairly popular. And you can see the reason why, because if you get lucky, there is a relationship between the value and the error of your approximation. But unfortunately, since we don't know M1 in applications, we don't really know what's the actual relationship. So also the third condition, although it looks like a good idea, actually does not work reliably. What we don't really like in all these pictures is flat functions. First of all, if the function is flat, then we cannot make a good bound on the derivative from below. And the relationship between the value and the error gets really murky. There could be a big difference between them, so the last condition doesn't really work well. In particular, imagine that the root r is a root of higher multiplicity. Roots of higher multiplicity have this unfortunate property that the derivative there is also 0. So in fact, we cannot make a reasonable lower estimate. The only estimate that works is 0, and if you put 0 here, we get infinity, and nothing useful comes out of it. So again, the second time we see it, roots of higher multiplicity cause troubles. They are really bad. And also you can think of this picture. That's a function which is very flat. It has a root r over here. Now I started here, and I'm doing, let's say, the tangent line method, the Newton method. But this actually applies to any iterative method. There are many methods that are looking for the root, and most of them have the form that we are producing successive iterations, successive approximations. And they all share the same problems. How do we stop? How do we control the error? So, some method, I don't care which one, it's approaching the function, and we are waiting for the value to be small, which happens, let's say, here. But we are still very far from the actual root. So the third condition is also not very good. So none of the 3 conditions works reliably, which people sometimes solve by, let's say, using the first and the third. They want both of them to be true, and they are hoping that things get good, but they won't. That's a problem. So I'm looking at a function which is actually e to negative x, and I shift it down by a little bit. So it does have a root. I asked for a stopping condition or stopping criterion to be the value. So this run stopped after 2 iterations and suggests that perhaps 2.99, which is like 3. So perhaps 3 is the root. Is that true? How do we find out? We don't have any control over the error. There's actually a fairly simple test. And it's a common sense test. Let's say that you are trying to find an approximation and you come up with some number. But now you are supposed to somehow guarantee that the error of this approximation is less than epsilon. Can you somehow guarantee it? Well, you can try this thing. You move to the right and you move to the left by epsilon, and you substitute into a function. Now, if you get lucky, you will see different signs. And if you can see different signs, then you are guaranteed to have the actual root here, and the error is definitely less than epsilon. So that's a very nice, simple test. And I'm actually quite fond of this test because you don't need any special theory for it. You don't need any special tools. You can use it with any method. Each time you come up with approximation of a root, you can simply test. And if you get lucky, you get confirmation that your guess is good. Now, if you have, unfortunately, the same signs, this can happen, then this doesn't mean anything because the root can be here if the function goes like that. So again, it's a test which is not perfect. It's not an equivalent test. It just gives you good information if you're lucky. Otherwise, it doesn't give you any information. And as usual, case of parabola, this test does not work well for roots of higher multiplicity. But anyway, let's try to apply it here. So I'm going to store this answer, this 2.999 something, and I'm going to evaluate at the root, and also I shift up and down by 0.1 because that's the tolerance that I'm using here. I'm very tolerant here. 0.1, not a good precision. Anyway, I got 3 positive numbers, which is not very good news. It could be that the root is there, but I know that it's not there because e to negative x, we know how it looks like. It's a function that looks like this. And I shifted it down, so there is a root. So let's try another. What if I put the relative error? This time, the algorithm ran a little bit longer. Now, is it a good news or bad news? That's a good question. Now, by changing the stopping condition, I am not changing the numbers which are produced by the algorithm. So when I was running the value stopping condition, we got the same 3 numbers, these 3 numbers. Now, if the algorithm is doing its job well, the successive numbers are actually better approximations of the root. So if the algorithm runs longer with more steps, it's actually giving me a better answer. So in this particular setting, short run means lower quality of the approximation. So I don't want shorter runs. Here I got a longer run, so I think that this approximation is better. Now, I used relative error. What does it mean? I'm essentially asking for the absolute error to be less than epsilon, but not by itself. I'm dividing it by the approximation, which is about 8. So I'm taking the absolute error, dividing it by 8, asking it this, well, actually, this is the thing. This is not the error, this is the difference. Let's call it D. This is the difference between the last 2 approximations. The difference between last 2 approximations divided by approximately 8 is less than epsilon. That's the condition which got triggered in the last line. And I have approximation 8.5. Now, is it a good approximation? Let's run my test again. I got 3 positive numbers, so I'm still here. I'm still here on the curve. I didn't get far enough. Now, what happens if I change this condition to absolute difference? Let's think about it. The relative difference is dividing this distance by 8. So I'm helping it to get small. I'm helping it to stop earlier. If I remove the 8, I am forcing the algorithm to work harder. So generally, I expect a longer run in this case, when I'm dividing by a number larger than 1. That's important. So I expect a slightly longer run. Let's see. Yeah, 11 iterations. Before it was 8, I think. So I got a new estimate. Let's have a look at it. Is it good enough? Yeah, I got a change of sign, as you can see. So now I know for sure that there is a root within 0.1 of this approximation. So you can see that in this particular example, the absolute difference worked best. But there are examples when it doesn't work best, so you never know. Okay? By the way, let's say that for some reason we decided to stick with the relative error. And we found that the run wasn't long enough. Can we help it? The answer is yes, we can change the tolerance, but only in the procedure. So we force it to run longer. So I improved the tolerance by 1, 0. I lowered the tolerance 10 times. I'm forcing the program to run longer, and the new result, but checked with the original epsilon, because that's what the customer wants. So now, now I got confirmation there is a change of sign, the last two values. So now I know for sure that I reached the right approximation. It's good enough. Okay? So this is a very important question of stopping conditions. 3 of them, none of them reliable, so we are just playing it by the ear. And there is this little test which I really like. Surprisingly enough, I don't find it in books, typically. Okay, so that's the error control. Fast. Let's talk about the speed of the algorithm. We need room. Let's talk about the speed of convergence. That's actually a fairly general question. Imagine that we have a sequence, and the sequence converges to some number. And we can ask, that's a natural question, how fast does this convergence happen? And when we think about it, we can just look at the difference and ask, how fast does it go to 0? So we can focus on sequences that tend to 0 and introduce some notion that would measure the speed of convergence. Now, in the context of numerical analysis, we would call this EK, that's the error. But we can simply see it as a difference. How do we measure speed of convergence? And it turns out that a good idea is to compare improvement of one iteration or one step in the sequence. We look at the error at a certain stage, we look at the next one, we compare them. We did exactly the same in that experiment in the chart that we can see over there. There we actually asked for increased precision and we asked how many iterations it took. But the same experiment can be interpreted the other way around. We can look at one iteration and see the improvement. And it's natural to somehow compare the errors. And we saw something like that before when we were exploring the bisection method. We saw that the error k plus 1 was bounded by 1/2 of the previous error. Actually, there we talked about the estimates for error. But let's keep it simple. Let's imagine that these are the errors now. That's the kind of relationship that looks hopeful. Let's see. In general, we would like to explore comparisons like that. Now, let's make a little experiment about the impact of such a relationship on the error. So we start with error AK, or EK, which is 10 to negative 4, which is 0.1, 2, 3 zeros, and 1. What happens after we pass to the next stage, to k plus 1? Well, EK plus 1, we just divide by 2, and we get 0.000, and divide by 2, so it's 0.5. Let's make the next step. Okay, how much room do I need? About this much. So let's have a look at the error EK plus 2. It's 0.1234 zeros, and then 25. We talked about correct digits, so just out of curiosity, we have 3 correct digits here, 4 here, and 4 here. Now we know that with bisection, we can expect 3 correct digits for every 10 iterations. So that gives us sort of like an intuitive understanding of the speed of convergence. And we commented that this is really slow. So let's say that we want a faster convergence. How can we force it? And the natural idea is that we make C smaller. So let's say that we can somehow arrange for this inequality to become, let's say, 1/5. That's a nice number to work with. For instance, we can take bisection. We can take the basic interval, but instead of dividing it into halves, we can divide it into 5 subintervals and pick the one where the sign changes. Quintersection, whatever, okay? So we just imagine a method like that. Now, how would the error react to such a relationship? Again, we start with 10 to negative 4. So we have 3 correct digits. Then we divide by 5. We get 0.00002. 4 correct digits. And then for the next stage, we still have to divide by 5. So it's 0.1234. And now we divide by 5 here, and we get 04. So it's 5 digits. Well, it seems that we are getting 1 new digit with every iteration. Actually, it breaks down after a while. We can make an analysis similar to the one that we made for bisection. And it turns out that for every 10 iterations, you get 7 new digits correct. So this is a definite improvement. Here it was 3 per 10. Here it is 7 per 10. So it's better, but it's still not a speed demon, because you are still adding new digits as a steady rate, essentially. And it turns out that this is not enough. We can do better. So the constant c is not the place where we should focus. We should focus on the exponent. Now you can say, okay, there is no exponent. Well, there is. There's exponent 1. In general, I can try to raise it by some means, and we will talk about it soon. So just out of curiosity, let's imagine that we can somehow improve power 1 to power 1.5. And I'm going to ignore this constant to make my life easier. And in fact, it's not really crucial. We will see it soon. So let's imagine that there is power 1.5 here, which is 3 over 2. So we should take square root and then cube. The starting error is 0.123 zeros and 1, just like before. Okay, the next error, we take square root, which is 10 to negative 2, and we raise it to power 3, which is 10 to negative 6. Perhaps I will make a little note here. This is 10 to negative 6, which means 5 zeros. 1, 2, 3, 4, 5, and 1. The next stage, we take square root, which is 10 to negative 3, and we cube, which is 10 to negative 9. So it's 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and 1. So when you look at the number of zeros, now it goes 3, 5, 8. And if you try the next step, it will be even more, the difference between the two successive number of zeros. So here the zeros, or the correct digits, are not increasing in a linear fashion, but much faster. This is a much better convergence. Of course, the question is whether we can find a method that works like that. Very good question. Let's be super optimistic. Let's imagine that we can find a method which actually has exponent equal to 2. What happens? Well, the start of error is 0.0001, just like before. 3 correct digits. We square it, and it becomes 10 to negative 8. So it's 0.1, 2, 3, 4, 5, 6, 7 zeros, and 1. And then we square it again. This becomes 10 to negative 16. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 1. Ooh. Okay. 15 correct digits. And you can see that the number of correct digits actually doubles, or better than doubles, with every iteration. Now, of course, it may happen that there will be some constant c, which may slow it down if it's larger than 1. But the substance stays the same. If we can increase the exponent in this relationship, then we definitely do get much better convergence, much faster convergence. And that's the general idea. Let's codify it. Let's have a look at some definitions. Here we go. We have a sequence. Do we? Yeah. We have a sequence which converges to some x infinity, and we are keeping track of the difference. Okay, here for some reason I put the difference the other way around, but since it's in the absolute value, it doesn't really matter. And we say that the sequence converges with order q if we have an inequality which looks exactly like this, and the power q is here. And this is sometimes called the q order of convergence. Now, we are going to apply it to our methods for finding roots. And we already had one, bisection. And for bisection, we could not really determine relationship between actual errors, but we could determine relationship of this form comparing estimates for errors. And this is happening in general as well. So there is an alternative notion of order, which is the second paragraph. And it says that a sequence converges with order q if we can find some upper estimates for those differences, and those upper estimates actually converge with q convergence. So we have two notions of convergence, of speed of convergence for sequences. And there is a theory about it, and those two notions are not the same, but they are related and so on. This can be done. But in numerical analysis, we do not really have to worry too much about it because we essentially do not have a choice. We were exploring the bisection method, and then we were able to establish relationship between estimates, and relatively easily, but we were unable, for obvious reasons, to establish relationship like that for the actual errors. So we didn't have a choice. We were forced to adopt the second version, the R rate. And the new methods that will come today, they are of the opposite type. We will not be able to see some natural estimates for the errors. And we saw it that we have no control over the error for the Newton method. So the second definition is not good for us. But remarkably, although we do not know the errors, we can actually establish, and you will see it soon, relationship of this form for the actual errors. So quite naturally, we use the first version of this definition. So for each method, one of these two will be natural, and the other one will be more or less impossible. And since we don't have a choice, we don't have to worry about it. We just say order of convergence. Which brings us to the definition. We have a method, and it's an iterating method, and it's not really crucial that it produces a root or that it's attempting to produce a root. This can be any iterative procedure which is trying to produce some quantity or approximate it. So we have some quantity that we want to find, and we have an iterative method which produces approximations, which hopefully are better and better. And we can ask, how fast does it get to really good approximations? What is the rate of improvement of such a method? And we naturally look at the sequences which are produced or generated by this method, and we apply the new notion to them. This looks natural. However, there are some little problems that we have to handle, and they make this definition a little bit, let's say, less transparent or less nice that we would want it to be as mathematicians. The first problem is roots of higher multiplicity. They are really troublesome. We saw it, and we will see it repeatedly. So if we just said, okay, the speed of the method is determined by how fast those sequences go, the roots of higher multiplicity would spoil it for us, because they would force us to say, okay, all the methods go as fast as the bisection method, essentially. So if you want to see the true strength of a method, we have to disregard the roots of higher multiplicity. They are causing trouble anyway, we know it. And ask about simple roots, because there we see the strength of the method. So that's the first restriction. Let's see. Whenever this method produces a sequence converges to a certain root, and this root is simple. That's the key assumption. And essentially, this is a typical case. So we can say that we are focusing on a typical case when our method produced a certain sequence of approximations. And then we want this sequence to converge with rate q. Now, establishing a relationship like that requires some assumptions. This requires some analytic work with functions. And if you want a better result, you need better tools, stronger tools for that, and you need the functions to be nice. So that's the second requirement here, which is not exactly mathematically precise. It says, assume that the function is sufficiently smooth. Now, the question is what's sufficiently? And the answer is for each method, it means something slightly different. So this definition is not exactly correct from a mathematical point of view, but it works, and it's the best we can do, essentially. And we will see those assumptions, how they come up very shortly. So that's how we judge methods. We disregard the bad case of higher multiplicity. We disregard really badly behaving functions. So we look at typical nice behaving case. And then we ask, okay, what's the rate of convergence? And there are some interesting examples here that show that we would really love to have high exponent in those estimates. Let's have a look at some results that we already do have. And this is the obvious one. It's about the bisection method, because there we had an estimate like that. And the last sentence is important. The bisection method is of linear order, which means of order 1. So methods of order 1, these are the slow ones. And for methods of order 1, the constant c is crucial. Here is a new one, and that's the key result for us. We have one paragraph of technical assumptions, and I will get to them soon. And then it comes. We have a sequence generated by the Newton method. And then for the sequence, we have two interesting estimates. And the first one is the key estimate that we want to see. On the left, I can see the error of the k plus first iteration. And on the right, I see the error of the kth iteration, and I can see power 2. So the Newton method is method of order 2. This is it. And that's what people know about the Newton method. Intuitively, if you use it, and if you have a convergent situation, then the number of correct digits doubles with every iteration, more or less. It can be even better, sometimes a little bit worse, depending on a constant c. We can see the constant here, m2 over m1. So, let's fit it with the general framework. Now, we should disregard roots which are not simple. And we should perhaps disregard functions which are not all that smooth. That's the general definition for the order of the method. So let's have a look at it. What's the assumptions? We need a function which is twice continuously differentiable on some neighborhood of the root. That's the sufficient smoothness. We need two derivatives to play with. Then there should be some constant. What are they doing? The first constant, m1, is pushing the first derivative away from 0. Now, we already saw this assumption. And we know that this assumption is exactly related to the multiplicity of the root. If the root is simple, then this m1 will exist. If the root is not simple, we are out of luck. So this is the connection with multiplicity of the root. The second constant m2 is an upper bound for the second derivative. Now, if the second derivative is continuous, we can find this bound. So you can see that those m1, m2, they are not really bringing any new requirement to the game. They are just collecting information. The core requirement is that the function is twice continuously differentiable and that the root is simple. These are the two assumptions. And they exactly fit with the definition of order. And then we get that for convergent sequences, we have exactly order 2. Wonderful. Newton method is fast. And now we have confirmation. How about the second inequality? Well, I look at it, and on the left I can see the k plus first error, which is interesting. And on the right I can see square of something, of the absolute difference. That's the favorite stopping condition. So the second inequality is interesting because it relates the stopping condition that we like to use with the error. This could be useful if you can get the constants m1, m2. Very often you don't have them at all. But if you have them, you can actually see a relationship like that. And in a way, this is a justification why this absolute difference may be a good stopping condition. It really does have something to do with the error. By the way, I didn't talk about it earlier, but when we use the bisection method, we have a certain generation here, xk, yk, or I think we called it ak and bk. Doesn't matter now. When do we stop? Well, we stop when half of the interval is less than epsilon. What is the half of this interval? Well, there is the new generation. This point was called mk. And now here is the point called mk plus 1. It's in the middle. And one of these two previously was mk minus 1. So when we are talking about half of the interval, half length of the interval, we are actually comparing the latest two iterations. So the stopping condition for the bisection method is really just an absolute difference condition. So that's another justification why the absolute difference is a good idea, because for the bisection method, we were actually using it without really knowing it. Okay, so that's regarding the order of the method for the Newton method. It's very fast, it's very nice. Perhaps I should make a little clarification. For a Newton method, we have an estimate like that with power 2. We talked about the order of the method before, when we were solving differential equations numerically, when we were doing integrals numerically. And there the inequality was similar, but at the same time different. Why? Well, the similarity lies in comparing error and having power. And we like powers which are high. That's the common part. The crucial difference is that the setting is entirely different. With those previous methods, we were always constructing just one object. For instance, for the integral, we just summed up, let's say, rectangles, and we got a number. And to construct those rectangles, we needed to choose a step of a method. And then we ask for the error as it depends on the step of the method. So we construct one object, and then in constructing it, we use a certain step size, and this compares with the error. Here, this is an entirely different situation. We are not constructing one object, or we do, but we do it repeatedly. So we construct the same object again and again, approximation of a root or something. And we do it repeatedly, and there is no step, because we are not using any steps in constructing this sequence. So these are two totally different situations, but we end up comparing with power skew, so that's the common part for the order. So there are two different settings for the order, and it's good not to mix them up. Okay, let's try some experiments to see how this actually works out. We have a little code here, and there's a polynomial x times x minus 2 times x plus 2, which has really obvious 3 roots. Let's make a little chart. So there is root negative 2, there is root 0, and there is root 2. And the polynomial starts with x. That's important. You will see why in a second. And now we'll try to get to these roots using the Newton method. The starting point is 0.7, and the tolerance is 0.0001, 10 to negative 4, the traditional tolerance that we use in this lecture to keep things comparable. Here we go. So we got to the root 0 in 4 iterations. Now let's see what happens if we start at 1.7. So perhaps I should make a note, because these are all important factors about the starting points and also about the tolerance. When we start at 1.7, we get to the root 2 again in 4 iterations. And finally, we try negative 1.7. And we get to the root negative 2 in 4 iterations again. Now, this is not really surprising, because this formula is actually symmetric about the origin. So all the situations should be symmetric, and the calculations for 2 and negative 2, they should be identical up to a sign. We will see. Now, what I'm going to do, I'm going to raise the power at x to x squared. What happens? Well, the root 0 now has multiplicity 2, and also the shape changes. And let's run the same experiments again. I start at negative 1.7, I run it, and we got 5 iterations needed. So that's the reaction of the Newton method to the change of the function. If I use 1.7 as a starting point, it should be 5 again. Yep, it is. Now the procedure is actually telling me that most likely we found the root. That's a little bonus which I programmed into it. The function value comes up 0 in the computer precision. But this is just of passing interest. Here it comes, 0.7. 0.7 gets me to the right root, 0 in 13 iterations. Now, what can we say from this chart? And the answer is actually not very much. One could say, okay, this number 0 is definitely worse now compared to the other iterations. But this is just one experiment, and one experiment doesn't really tell you much because the shape of the function changed. And a method reacts to the shape, for instance, by being slow at the start. And that's not what the rate of convergence is talking about. Rate of convergence is about the improvement, the quality of improvement. And what happened here? Well, it could be that perhaps the method took some steps just to orient itself, just to look around and see how things are working. So the real appreciation for the speed of convergence comes when we now improve or sharpen the tolerance, when we ask for a better result, more precise estimate. And we will see how many iterations are needed for this improved precision. So from 10 to -4, we will pass to 10 to -7. And now we will start seeing things, hopefully. So I will go back to x with the power so that we don't get our surprise spoiled. And I will improve this to 10 to -7. And we see, okay, five iterations, that's the change if I improve the precision. So we needed one extra iteration. If I use 1.7 as the starting point, I should get to 2 in 5 iterations again, and it will be the same here, symmetry. So we can say that one iteration was enough to improve the precision by 10 to -3, or perhaps even more. We don't know it precisely, but roughly that's what we can expect. Now let's change the power to 2 again. So that's the x square polynomial. We start at 1.7, I fire it up, and I get 5. So we need 5 iterations, also for improved precision. This is interesting. How is that possible? Well, actually, with 4 iterations, the error was still too large for the first tolerance. So the Newton method was forced to go to the 5th iteration to satisfy this requirement. But the improvement was so good, such a good improvement, that it also automatically satisfied this new tolerance, this new requirement. So we can see a really fast convergence here. Just one iteration does a big improvement. Now here comes the interesting part. We start at 0.7 and we get 23 iterations. And here is where you can see the slow convergence. This is the convergence which is quadratic, order 2, very fast improvement of precision. And this is a linear convergence. We needed 10 iterations, 10 more iterations to improve precision by 3 digits, which is comparable to the bisection method, essentially. And that's about it. This confirms the theoretical results. And it confirms our feeling about the methods as we see them. When you compare them, you can see that the bisection method and the Newton method are complementary in a way. For each of the 3 properties, always one of them is good, the other one, well, let's say not so good. So they complement each other. And you could also say it in this way. Newton method is really, really fast, but it pays for it by reliability, by missing control of the error. So if you want something, you have to pay for it. That's normal. It's the trade-off, classical trade-off. I've been saying some, let's say, not so complimentary things about the Newton method. Like it likes to go around, it can get lost, things like that. But it is fast. It is really fast, and we can make it work reliably with a little preparation. So this is a really very good method. The second big advantage is that it can be actually used to prepare iterating schemes that we can then use without really worrying about Newton method. We can get general formulas, iterating formulas for specific problems. And I will show you examples like that in the bonus video. The third big advantage of Newton method is that it's flexible. It can be adjusted to more general settings. For instance, it can work in more dimensions, which is very useful. In fact, the Newton method is probably one of the most popular tools for finding roots and similar solving similar situations in more dimensional cases. So the Newton method is really powerful. One just has to be careful when you work with it. Let me show you one example. Here we go. We have a quadratic polynomial here, and we ask the Newton method for the root. The usual tolerance, 10 to negative 4. Here we go. Division by 0. That's one of the problems I've been talking about. At point 2, the derivative is 0, and we try to divide, we are in trouble. Well, never mind. Let's start someplace else. Let's say 1.3. That's a nice starting point. It's almost 13. That's interesting. After 50 iterations, the procedure gave up and tells us, okay, don't take the answer too seriously. I gave up because it's simply running too long. Let's see what's happening there. Let's take it from the start. We start at 1.3, we go to 2, and then we go to 0, then to 4, or almost 5. Then we go to 0, essentially, then to 7, then we return back to 2, 8. We are going right and left, right and left. We are swinging from side to side without really ever going anywhere. Here we are around 0 again, here we are around 8. For an experienced Newton user, this suggests the following shape. It's a dip, and we are going around this local minimum with our tangent lines. And actually, this is what's happening here, exactly. However, this is a quadratic polynomial, so it must have a complex root somewhere. But of course, Newton cannot find it because we didn't introduce any complex units into the picture. So let me introduce, let's say, plus I into my starting point. So now the starting point is 1.3 plus I. And once there is some complex unit, Newton switches to complex calculations. And let's see, well, let me restrict the digits so that we can see it properly. 4 digits will be enough, I think, on the output. Yeah. So we can see that Newton now works with complex numbers here. And after 5 iterations, because it's a fast algorithm, it found the root 2 plus I. And that's actually the correct root. So you can see that the Newton method also handles complex numbers easily. Very nice. It is a very nice method. It's fast. I talked about some disadvantages, but okay, these can be handled. By localizing the root, for instance, you can print out the function, then you look at it, you say, okay, the root is roughly here, and then use the Newton to identify it almost precisely. However, there is one, let's say, structural disadvantage or conceptual disadvantage. If you want to use the Newton method, you need to know the derivative of your function, but this is not always possible. Now, for a student of calculus, this sounds weird because you have a function where you differentiate it. But in applications, very often the function is not given by a formula, but for instance by some procedure that you have to follow to get the function value. It may be even worse. The function may be given by a result of an experiment. For instance, imagine that you have a wing and you have a wind tunnel. And you position the wing into this wind tunnel and you can change the angle of attack, as they call it, which is this angle. You can tilt the wing and you start the experiment. The angle of attack is alpha. And you measure, let's say, the air resistance. Or you can measure the lift of the wing, as it depends on the angle of attack. And that's your function f. So every time you need to know the value, you have to run an experiment, which is a question of a few hours, perhaps. I can invent stories like that, which are even worse. Let's say that alpha is the temperature in a greenhouse, and F alpha is how many tomatoes grew actually over the summer in your greenhouse. So to get one value of F, you actually have to wait one season, essentially. So each calculation of F can be very, very expensive, but the main thing is you don't have any derivative. And then the Newton method, although it's nice and fast, cannot be applied at all, for principal reasons. So here is a good question. Can we find a method which will be better than linear? Because we Okay, we are not modest anymore. We want a method which is faster than linear. Can we find a method which is exponent or order better than 1, but without using derivative? That's a good question. And to see that, we need a lot of room. Let's erase.